Hi class. So in this video, let's look at an example of prefetching that will again help you with one of the problems on homework 2. Okay, for prefetching, let's examine the following code. It's a simple nested for loop where you're just iterating through elements of an matrix array of a 64 cross 64. You're just looping through each of the element and just finding that sum. Okay. So assume that for this problem, the integers I and j used within the loop counters and the sum itself are registered or in the processor. And the only time you're accessing a data cache is for loads of or reading of the matrix element aij itself. Okay. And then let's assume certain other things like int and float are of the size 4 bytes of data. Then we have a fully associative data cache with 32 lines or sets or indices, and then each line, meaning each cache block, has 16 bytes size. And then let's also assume certain other uh, parameters like executing the for loops itself in line 1 and 2 take 2 cycles. Executing the addition operation in itself in processor takes around let's see, 5 cycles. Uh, and then in case if there is a data cache miss while accessing aij, we end up taking uh, 40 cycles. Okay. So now let's see initially what is the cost or how many cycles does it take for this code fragment to just execute without any prefetching, right? Let's just look at that. Okay, so let's go ahead and start populating that. For ease, let me copy this code snippet here and then write down the costs. Line 1 takes 2 cycles. 1 and 2. Line 3 takes 10 for add. Oh no, sorry, 5 for add, I think. Let's see. Yeah, 5 for add and then 40 for miss. Okay. Let's see. What else is needed? There is a bit about cache configuration, but let's not bother about it right now. Okay. Let's start looking at the operation itself, right? So first, the line 1 is going to be executed 65 times, right? Like from 0 to 63, because the I will be true. And to validate whether I is less than 64 or not, it would be executed one more time. So line 1 is executed 65 times. And the cost is 2 cycles. So the overall cost is 130 cycles. Now for line 2, let's see. Again, the same thing, like the J loop itself is going to be executed 64 times and then one time to check whether J is now less than 64. But this in itself is going to be implemented 64 times for each of the I, right? So this will be 64 into 65 into 2. So that is around 8320. Okay, then let's look at line 3. So for line 3, let's not worry about the misses or hits right now. Let's just look at um, the base addition itself. So this again is going to be executed. So the sum is going to be executed 64 times for each of the j loop, and then that is nested in another 64 of the I loops. So this is executed 64 into 64 times, and the cost is 5, right? So that is around, let's see, 20,380. Okay. Now, now we have to worry about what are the hits and misses, right? Uh, okay, so for that, let's look at the cache configuration that is given to us. So what we know that each aij, because it's a float entity, this is a 4 bytes. Now, our cache is a fully associative cache and of 32 indices, and cache block is of 16 bytes, right? So the fact that it's fully associative um, is helpful for us, and the fact that 32 lines is also that it's slightly bigger than what we need, so we don't have to worry about the cache configurations in terms of if there are going to be any evictions and stuff like that. It's fairly big enough for our experiment. um, but let's look at the cache block size itself, right? The cache block was 16 bytes, which means that in our very first unrolling of the loop, right? Let me copy this again here, uh, where I am working. Actually, let me get rid of these lines which I don't need. That doesn't help either. Okay, yeah. So we have so when we first access the element in the very first 0, 0th loop, we are accessing a 0, 0, right? um, because cache block is of 16 bytes and this is of 4 bytes. When we try to bring in data consisting of A00, we are going to bring in some additional data as well, right? So let's do the math for that. So because 16 bytes uh, can be broken down into 4 byte chunks, and we are let's assume that it's uh, perfectly mapping, right? So that if we bring in a 0, 0, we will bring in also a 0, 1, a 0, 2, and a 0, 3. So when we sort of execute the first time, the sum operation, our first entity 0, 0 is going to be a miss, but in the next, when we are trying to add 0, 1, it's going to be a hit. The same goes for 2, same goes for 3, but then again in the very next iteration, when we try to bring in a um, 0, 4, we'll see a miss again, right? So we'll bring that in, but along with 4, we'll bring in 5, 6, and 7. So we'll see a hit again subsequently for 3 iterations. And then in the fourth one, again for 0, 8, we're going to see a miss. So that means for this operation, um, in each of its, there is a miss every 4 of its accesses, right? So now if we try to calculate the misses cost for line 3, that would be 64 times into 64 times as usual, but here we will be having a miss every 4 times, and then because the cost of each miss is 40 cycles, so the overall cost incurred here now will be 64 into 64 by 4 into 40, which is around 40960, right? So total um, is going to be just an addition of all these four entities, which is around 69,890. Okay. Uh, I could have possibly added like one more line for hits, as in the cost being one cycle maybe. But for the timing, let's just ignore. Now let's look at it, what or how this code can benefit from prefetching. So in prefetching, what we can do is we can think of, since we know that there is a predictable pattern to accessing the matrix elements, we can insert a prefetch statement, either at software level as a programmer, or a compiler can sometimes do this for you, and prefetch certain elements. So for instance, here when we were bringing in A00, if we also brought in A04, the cost of bringing in A00 and A04 can sort of run behind the scenes, right? And while uh, the operations of some uh, uh, on 0001 and 0203 are happening, 04 can be uh, fetched, right? So let's try to rewrite this code to um, avail that. So let's uh, write the first for loop. Let just copy this. Here, uh, one thing that we want to do is we want to insert some prefetch statement here, right? So let's say prefetch some element. Uh, so because we already saw the pattern, right? Like when we are doing for 0, 0, we want to prefetch 04. So going by that, uh, it's probably going to be I j plus 4. Okay. And while we are doing the prefetch here, you don't want to keep prefetching every other iteration of j also, right? Like in if we try to unroll this is going to look like sum is equal to sum plus a 00, then 01, 02, so on, right? In each iteration. So if we had a prefetch here, in the 01, it's going to prefetch A05, which we don't necessarily need. This is unnecessary because the fetch of the prefetch of A04 here will anyway uh, bring 05 in the same cache block. So we are trying, this would be wasteful. So let's just go ahead and optimize that by saying that don't increment j every time with +1, but do it say with +4. And then we unroll these statements as uh, so Aij, ij plus 1, j plus 2, ij plus 3. So what we are doing here is uh, so in each we are slightly modifying the for loop to only increment in counts of 4, and then we've sort of unrolled that uh, uh, thing within the for loop body, whatever counts we were going to do here, so that now when j is equal to 0, you add a so a00, a01, 02, 03 here, and you prefetch 4. So in the next iteration, when j is equal to 4, you're going to prefetch 08, which is what we would want, and then here we would add 04, 05, 06, 07, right? So this fashion of changing the loop variables into the loop body is called unrolling, and this is most often used whenever we are trying to prefetch and rewriting the code. So now let's see the cost for the new modified code that we have. Again, for line 1, that doesn't change, right? We are going to execute it the same number of times and the cost is same. So this remains the same. Line 2, however, has been modified now. So now we are going to execute it only every 4 times. So that is um, 64 by 4, which is 16. So we'll do it 16 times for each of the 64 times of the I loop. Actually, I think we'll do it 16 plus 1 time because we want to see the last bit whether it was true or not, and then 2. So that is 16 into 64 into 2, right? Which is, oh, my bad, um, 17 into 64 into 2. So it's 2176. Then line 3. Oh, actually, I should rename these guys. Let's call this 3A, 3B, and 3C, 3D, and 3E. Okay, so let's look at line 3 A. So let's see what is the cost of prefetch cycle. Uh, okay, so the prefetch cycle to execute in the processor itself is going to take 1 cycle, but if there is a data miss for the prefetch entity, again it's going to take 40 cycles. So because let's just look at it. So when we issue the prefetch for the very first element in 3A, that is for A04, obviously this would be a cache miss. So this is going to be a miss, and so this will incur a 40 cycle penalty. And then for the sum Aij, it's again going to do, because 00 is going to be a miss. So it will be a miss and incur 40 cycles of penalty. But these two guys will sort of overlap, right? Like this will be issued probably in cycle 1, so in cycle 2 this is going to be issued in the cache. So uh, a bulk of these 40 cycles is going to be overlapped. So we don't have to count the miss individually. We can just count one of the misses. Say, let's say we are going to count the miss for 04. Okay, and so and once both of these things are fetched, we'll go ahead and execute the statements 3b c d e, and in the next iteration when we are actually going to do sum of 04, 05, 06, 07, because of the previous prefetch, this data is already brought in, so there will be a hit, but the prefetch for these guys is going to be by I j plus 4 is going to be 8, right? So A08 is going to be a miss again. So A08 is going to be a miss in the next iteration, but for executing the statement add of 04, 05, 06, 07 individually are going to take 5 cycles each. So 5, 5, 5, 5. That's around 20 cycles. So this 20 cycles is actually going to amortize onto the uh, um, cycle effect of, say, uh, 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 is going to sort of hide the 40 cycle latency of the miss. This is going to be 40 cycles, but behind the scenes you will be executing 20 cycles again. Uh, so 20 cycles out of this will be consumed for 3 B to E. So the only cost left is 20 cycles, right? So for um, 3A, uh, the very first one is going to be completely amortized. Not exactly, actually, it's amortized with 3B, yes. So we will have one complete miss of 40 cycles, and then subsequently we will have 64 into 16 um, 20 cycle cost, right? As far as the miss is concerned. And let's see, this is for the miss. But the line 3A in itself is going to be executed 16 into 64 times. And its cost is just one cycle, which is 16 into 64 is 1024. And then for the misses of line 3A, it's going to be 16 star 64 star 1 star 40, which is wait a minute, it's actually not 16 times, it's just for each of the I loops, right? Yeah, sorry, my bad. It's not going to happen. Like there is one cost for the 04, but this cost is going to be amortized for 08 and so on. But again, for A14, there will be a cost, but then 18, 12, and so on, the cost is going to be amortized. So it's actually just one time thing. So it's 64 into 40, which is 2560, and then 64 into 16 into 20. So that is 64 into 16 into 20, which is 20480. Now for lines 3B, 3C, 3D, and 3E, then not going to be any misses because the 00 miss is going to be amortized with the prefetch of 04, and then subsequently everything is prefetched. So all of these can actually execute um, as if there was a hit. So we will just take the penalty of, so there are 4 instructions in total which are of the same nature. These are executed 16 into 64 times, and then each one of them costs around 5. So this is another 20480, right? Okay. So now the total cost is, let's see, uh, this plus 2560 plus 1024 plus 2176 plus 130, which is 46850. So if you notice, this is significantly lower than what we first got, right? Yeah, this is the total that we had. Um, let's see. So let's see what's the speed up. So this is so 69890 by 46850 is around 1.4949, which is roughly around 1.5 times that, right? Which is really good speed up. So that's why in most of the modern processors, for very simple predictable loops like this, the compilers are optimized to automatically insert prefetching. And in cases where there isn't that facility, a programmer can simply look at it and sort of optimize it for prefetching. Okay, so let me go through the document of the homework 2 itself. So the first question on prefetching is very similar to what we did. So follow the same steps. Then the second question is about the inclusive, exclusive, and non-inclusive, non-exclusive cache configurations and how to populate them. This is also recorded in one of the other videos, so it should be useful for you guys to do this question. Then the third question is on the uh, uh, average memory access time, which is also covered extensively in the class by professors. So I'm not going to do an additional example on this because it should be straightforward. And then the fourth question is on virtual memory. This has also been explained in class quite well. So I'm not going to do a tutorial on this, but certain things that I would want to highlight is that when solving this specific problem, notice that when you are looking for virtual tags and or physical tags and things like that, originally you have your entire virtual address, right? Entire of your 0 to 30, let's assume 32-bit virtual address space. So you have all these 0 to 31 bits ready. So to figure out what so the there is something called as page, and like you access things at page granularity in an application, because the virtual memory is sort of um, laid out in chunks of page size. So if the page size is 4K, 4 KB, your page offset is going to be 0 to 11 bits. But this doesn't necessarily have to always overlap with your index and block offset, because block offset is going to is determined by your cache block size, and your index bits are determined by, again, cache configurations. So uh, even though there might not be a one-to-one overlap, because you have this entire virtual thing, you can actually, based on the cache configuration, figure out your virtual tag, virtual index bits, and the block offset um, straight away. But if you're looking at physical tag or physical index or any such things, you need the translation. So you will, again, there could be a one-to-one overlap where page offset is sort of containing the block offsets and the index bits, but it doesn't necessarily have to happen. So You first have to do a TLB lookup to get physical page number from the virtual page number. Once you got these bits, and with the page offset of the virtual address space itself, you can get your other bits of your entire physical address map. So the block offsets and index bits are determined by the size of cache, but the bits themselves can be directly taken from the page offset that was present in your virtual address space. And once you have this translation of physical page number to virtual page number to physical page number, you can get the physical tag, and if there are any index bits out of that. So that is one thing to notice. And then in when you're accessing TLB and cache, so you can access both TLB and cache in parallel if you have the required data to access a cache. And within the cache, you can access the tag side and your data side in parallel. Like as long as you have the index bits that you need, you can in parallel query the tag part and the data part. And then uh, once you have a hit and a miss, and like if you validated that, you can just mux now the data from the data side of the cache, and by selecting the right way. Okay, so based on that, I think you have rest of the information enough in the question to sort of solve this question. Okay, that's it for this video.